So hi all, I am Meet Sharma. This is ELP101 lab project on the topic Wien Bridge Oscillator circuit using op-amp 741. Now the first question that comes in our mind is what is an op-amp? Op-amp, short for operational amplifier, is an electronic voltage amplifier that is a very large voltage gain. It basically amplifies the difference between the two input voltages. That's why it is called a differential amplifier. It was initially used in analog computers. In analog computers, it was used to find the difference, sum, differentiation, and integration of the input voltages. It was first invented in 1941 by Carl D. Schwartzel of Bell Labs. Now, this is the circuit diagram representation of an op-amp, which is like a triangle. V1 and V2 are the input voltages. So the output voltages will be A times V1 minus V2. That is, it will amplify the difference between the input voltages. 741 is the IC number of the op-amp. Now this is the representation of a block diagram for an op-amp 741. Now op-amp is an 8-pin integrated circuit. All the 8 pins of the op-amp are shown. Here the input is given through the two pins 2 and 3. Pin 2 is used for the inverting configuration. That is when the output will be phase shifted by 180 degree. And pin 3 is used for the non-inverting configuration. That is when the output will be in the same phase as the input. Pin 7 and pin 4 are used for connecting a power, that is the DC supply into the op-amp. Now what is an oscillator circuit? An oscillator circuit is basically any circuit that generates an oscillating voltage signal without the need of any input signal. It requires only a DC supply. So basically it converts DC supply to AC supply. It is basically an amplifier with a positive feedback. The various applications of oscillator circuit are used in electronic devices like smartphones and laptops, etc. They are used in communication systems like radio, and they are used in signal generators, which are used in electrical labs to produce various kinds of signals. Now, how can we make an oscillator circuit using an op-amp? So the oscillator circuit using op-amp can be made by using the principle of positive feedback, in which some portion of the output is fed back to reinforce the input signal for the sustained oscillation. For example, if we initially apply a very small input voltage, then some portion of the output will be sent back to the input and again, and the input voltage will be reinforced. So there will be sustained oscillations at the output side. Now if beta, now the basic design of this circuit basically consists of a feedback circuit. Now the output is fed back to the input by the help of a feedback circuit which can consist of any kind of components. Beta is if beta is the ratio between the feedback voltage VF and VO, then the gain of this amplifier, that is the VO by Vn, which when calculated is given by A upon 1 minus AB, where A is the voltage gain of the op-amp. Now if we take the limit Vn tending to 0, because in reality we do not supply any input voltage to this oscillator circuit, so what we will get is AB is equals to 1. Hence for an oscillator, the Backhausen criteria is that the product of A and beta should be equal to 1, and the phase shift between the Vin and VO must be 0. Now this is the circuit for a Wien Bridge oscillator. The Wien Bridge oscillator basically consists of op-amp in non-inverting configuration. It is used to produce harmonic sinusoidal signals for a wide range of frequencies. It is based on design of a bridge circuit made by Max Wien. Now we see that basically the feedback circuit of a Wien Bridge oscillator, it basically consists of a RC circuit in series, of a series RC circuit and a parallel RC circuit. This type of circuit is used to feed back the output voltage to the input one. Now to find the value of B and A for a Wien Bridge oscillator, we try to solve the equations for a Wien Bridge oscillator. Now the op-amp is in non-inverting configuration. The gain A will be A is equals to 1 plus R3 by 4, because we know that in non-inverting configuration this is the value for the gain of an op-amp. Now for finding the value B, we see the feedback circuit. Now the feedback circuit is as shown. It basically consists of a RC circuit in series with a parallel RC circuit. Now we know that XC is equals to 1 upon omega C. This is the basically the reactance of the capacitor. Hence the series RC circuit will allow large frequencies to pass, while the parallel RC circuit will allow both large and small frequencies. Because if we see for the series RC circuit, if the frequency is very large, then XC will tend to 0, because it is inversely proportional. So this R circuit will be open circuited, will be closed circuited, sorry. Circuit. Now if we assume that Z1 is the impedance of the series RC circuit and Z2 is the impedance of the parallel RC circuit, now the feedback voltage VF will basically be given by the voltage division of VO, that is Z2 upon Z1 plus Z2 times VO. Now if we consider that X1 is the impedance of the first capacitor, 1 upon omega C1, which is equal to 1 upon omega C1, and X2 is equals to 1 upon omega C2, then what we will have is Z2 is equals to R2 star minus X2J upon R2 minus JX2, that is Z2 is the parallel combination of X2 and R2, and again putting the value of Z1 also, which is R1 minus JX1. On solving, what we will get is that VF is equals to R2X2 upon R1X2 plus R2X1 plus R2X2 minus J times X1X2 minus R2R1. Now at a particular frequency FR, the value of the amplitude of feedback voltage VF will be highest, and this is the only voltage which will be passed on easily by the feedback circuit. This frequency will be when the impedance is in resonance, that is the reactive part is 0. So taking reactive part as 0, that is X1 X2 is equals to R1 R2, what we find is that the resonance frequency will be equal to 1 upon 2 pi root over R1 R2 C1 C2. Hence by adjusting the value of R1 R2 C1 C2, we can change the frequency of the output signal. This fact is used to generate signals of various frequency in a signal generator. For example, in a signal generator, we can use the knob to basically tune the capacitance, and by tuning the capacitance we can change the frequency of the output signal. So here, hence the Wien Bridge oscillator can be easily used for the signal generator. Now the value of beta will be at resonance R2X2 upon R1X2 plus R2X2 plus R2X1. If we take R1 equal to R2 and C1 equal to C2, the value of beta comes out to be 1 by 3. And by Bragghausen condition, AB is equals to 1, imply the value of A will come out to be 3. Hence for sustained oscillations, 1 plus R3 by R4, that is A, should be equal to 3. This means that R3 equal to 2 R4. This is the required condition for R3 and R4 for the generation of smooth signals. Also, the op-amp is in non-inverting configuration. There will be no phase change between VF and Vn. Hence, this oscillator satisfies the Bragghausen criterion for the oscillators. Uses of Wien Bridge oscillator. Now a fun fact is that the first product made by HP, that is the HP 200A, was in fact a Wien Bridge oscillator. It was basically an audio oscillator that was used to test sound equipments. In fact, Wien Bridge oscillator was a research topic in the engineering degree thesis of Bill Hewlett, who is HP's founder. Other uses of Wien Bridge oscillator that it is used for measuring the value of the capacitance. It is also used to measure audio frequencies. So thank you all.